Hey guys, welcome to another lecture video for Chem 115. In this video, we are going to explore our use of the Henderson-Hasselbalch equation in a different manner. And we're going to go ahead and use the Henderson-Hasselbalch equation to be able to quantify the pH of a buffered solution after adding some amount of strong acid or strong base to it. And so I want to start off this lecture by revisiting acid-base neutralization reactions that can occur inside a buffer system. And so it's important for us to understand how to develop these chemical equations because they're going to serve the foundation of our calculation. It's going to help us organize our train of thought when we work through these more complicated word problems. So let's go ahead and start. All right. So to describe this image that we're seeing, we have a beaker on the left-hand side. And inside this beaker, it contains HA and A minus. And so HA in this case is going to represent a weak acid. And this weak acid can be any weak acid. It can be carbonic acid. It can be acetic acid. Hydrofluoric acid, the list goes on. And so A minus is going to represent the conjugate base of that weak acid. And if you guys recall from an earlier buffer lecture video, whenever you have a weak acid and its conjugate base, you form a buffer. And so the solution that you guys are seeing on the left-hand side is a buffer. So let's just say that you have this beaker filled with this buffer solution, and it's sitting on this lab bench's tabletop. And all of a sudden, you or your lab partner or your teacher adds in a strong acid. And so I'm going to go ahead and just write strong acid for now, and then I'm going to change my color real quick. And so let's just say that this strong acid is going to be hydroiodic acid. So we're going to look at HI. So we're going to go ahead and dump some HI, some hydroiodic acid, in our buffered solution. Now, if you guys recall the nature of strong acids will have a strong tendency to ionize or to dissociate, such that your hydrogen is going to be separated from your iodide. Now, remember that this is a moment in time, just a small moment in time. And so I minus is floating around and is going to, kind of bump into HA and A minus and all that stuff. And if you guys recall from an early lecture video, since I minus is the anion of a strong acid, that substance will, in this case iodide, will have no effect on the pH. And so what that's basically telling us is that when we're looking at these chemical reactions, we can go ahead and ignore any spectator ions. And so the only thing that we're really left to focus on is the proton that was separated from that hydroiodic acid. And so this proton now has an opportunity to interact with two types of compounds. It can interact with weak acid in this buffered solution, or it can interact with the conjugate base. And so if you guys know anything about acids and bases, is that acids always react with bases. And so it only makes sense that this H plus is going to react with this I minus, and it's not going to react with another weak acid. And so we have this proton as H plus that's representing our acid, and it's going to react with the weak base. And so whenever you have an acid reacting with a base, they kind of come together. And in this scenario, it's going to perform, or it's not going to perform, it's going to result in HA, which represents, according to our chart, the weak acid. And so the combination of a proton and that of the conjugate base produces the weak acid. And so how can we summarize this reaction? Well, simply put, we're going to go ahead and write hydroiodic acid, and it's going to react with A minus, which is the weak base, and then this is going to produce our conjugate acid, our weak acid, and another I minus. And so it wasn't really necessary to write the I minus, because if you guys recall, it ends up being a spectator ion. And so whenever you guys are reacting a strong acid to a weak base, you produce the conjugate acid. Okay. In this case, it's going to be HA, which, remember, it's the terms are interchangeable. We can kind of view it in reverse. So we can say that instead of it being a weak acid or a conjugate acid, it's a weak acid. Doesn't matter. The main idea is that we produce the conjugate of that specific substance that's reacting with. And so this is something that I want you guys to kind of keep in the back of your mind when you're trying to perform these reactions that's happening inside a buffered solution. And so this isn't the only combination. This isn't the only reaction that can occur. What if instead of putting in a strong acid, we put a strong base? And so we're going to go ahead and reset our beakers here. And we still have the same, weak acid, the same conjugate base, and therefore we have a buffer in this beaker on the left-hand side. So this is going to represent a buffer. And so what's going to happen when we place a strong acid, a strong base to this buffered solution? And let's say that the strong base that we're going to utilize is sodium hydroxide. And so we're going to go ahead and place sodium hydroxide inside this beaker. Now, if you guys remember the feature or the nature of strong bases is that we're going to get 100% or close to 100% dissociation, such that we get sodium ion kind of just floating, and we have this hydroxide ion that's also floating. All right, so let's go ahead and think about the chemistry. Let's start off by talking about sodium. And so, do you think sodium will strongly interact with either the weak acid or the conjugate base to produce some type of chemical reaction? And the answer is no. And so if you guys recall from both the first semester of general chemistry and in one of the lecture videos that I've discussed, since sodium is a group 1A element, we typically consider sodium as a spectator ion, meaning that it's just there. It's not going to really react with any of the substances that's going to produce a significant change in the composition of that solution. And so sodium is just there, it's a spectator ion, and it's not going to affect the pH of the solution. And so we can go ahead and cross that out. We don't have to worry about it anymore, and we can just focus on the second component, in which case it's going to be the hydroxide. And so this hydroxide is a base. And so if you have a base and it's placed in this buffered solution, what substance is this base going to react with? And once again, every time you guys have a base, it's going to react with an acid. And so the only acid that's present in this buffered solution is going to be HA. So remember, HA is representing our weak acid. Doesn't matter if it's weak or strong, just right now, it's an acid. And so here we have this HA, and we're going to react it with this strong base, hydroxide. And so what's going to happen is that this lone pair is going to kind of pull in that hydrogen towards itself, such that this H is now going to be found with OH, producing H2O. Okay. Maybe I should do this in a different color. Okay. So I have oops. Oh no, I was right. So here we have this HA, and then we have the OH minus. And then this hydrogen is going to go to this hydroxide. And what we get is water. And so what we have left over is simply A, or A minus, which is going to be the conjugate base of this weak acid. And so once again, we need to kind of summarize in one nice chemical reaction what's going on. And so if we're starting off with our reactant, we have sodium hydroxide. And according to what we kind of went over, this sodium hydroxide is going to react with a weak acid. And so remember that sodium hydroxide is our base, so it only makes sense that it's going to react with an acid. And so the only acid that's available in the solution is going to be our weak acid, HA. And so very similar to what we did in the beaker, we're going to go ahead and ignore this sodium. And so our net chemical equation is going to be this OH minus, and then if you perform the acid-base reaction, this hydrogen gets transferred over to this hydroxide, producing water and A minus, which is the conjugate base. Okay. And so we're going to use these generic chemical equations that we've kind of derived by looking at the chemical reactions that's occurring inside this solution. Okay? So we always want to keep these two reactions in the back of our head when we're performing these types of acid-base neutralization reactions inside a buffer. The last item that I want to discuss before we start looking at problems is more or less a revisit of the Henderson-Hasselbalch equation. So if you guys recall from the last lecture video, the pH is equal to pKa plus the log of the concentration of the conjugate base over the weak acid. And so remember that when we were going over monoprotic acids and monoprotic bases, like the calculation of the pH, remember that pH is representing the concentration of hydrogen ion at equilibrium. And so that that little piece of information doesn't go away, right? So that still holds true for the Henderson-Hasselbalch equation, such that the concentration of the conjugate base must be at equilibrium, and the concentration of our weak acid must be at equilibrium. And so remember, we're describing the pH, which is at equilibrium. So all of these terms must represent equilibrium values. And the reason why I bring that up is because it brings back the idea of using an ice table. And we're going to go ahead and utilize this ice table just in a slightly different manner to determine the ratio of the concentration of the base to that of the acid. All right. And so I think we've built up a good enough background information that we can go ahead and look at the first word problem. And so what we're going to do is we're going to calculate the pH of a solution if 5 mils of 0.500 molar sodium hydroxide is added to a beaker containing 20 mils of 0.50 molar benzoic acid. And so it turns out that the acid ionization constant Ka of benzoic acid is 6.46 times 10 to the negative 5. All right. All right. So let's go ahead and summarize everything here, everything that we see in this problem through a picture. This picture is going to always help us develop our foundational chemical reaction, which will help us, once again, to organize our train of thought and calculations and et cetera, et cetera, et cetera. And so we have this beaker, and the current contents of this beaker contains a volume. So the volume is 20.0 mils. And we have a concentration of 0.500 molar of benzoic acid. And benzoic is going to be C6H5CO2. Okay. And then according to the problem, we're going to add 5 mils of 0.500 molar sodium hydroxide solution to it. And so we're going to go ahead and draw a little arrow here, and we're going to tell ourselves that we're going to add 500 milliliters of a concentration of sodium hydroxide that's 0.5 molar. And we're going to make sure that we're going to write the identity. And so if you guys can imagine, when sodium hydroxide is placed inside this solution, just like what we did in the previous section before we started this problem, we realized that sodium is going to be a spectator ion. And so really we're only working with a hydroxide. And what we're going to do is this hydroxide is going to react with this acid. So this hydroxide is a base, and this substance, I mean, if you look at its name, it already says it's an acid. Okay. And so what we're going to do is we're just going to write the chemical reaction that's going to occur between the two. And so we have this hydroxide that's going to react with HC6H5CO2. Now, whenever you're looking at an acid-base reaction, you always want to identify the ionizable hydrogen. And so typically when an acid is written, the first hydrogen that you guys see is the ionizable hydrogen. typically. Sometimes this hydrogen can be written at the end. Okay. And so what that tells you is that this hydroxide is going to pick up this hydrogen, and the outcome that we're going to get is water. That's liquid in state, and a conjugate base. So this is a weak acid. And how I knew that this was a weak acid is by looking at the Ka. Notice that Ka is far, far less than 1. Give me a clue that this substance is a weak acid, not a strong acid. And so if we extract a hydrogen out of the weak acid, we're only left with C6H5CO2 with a negative charge. So this is going to be our conjugate base. Okay. Awesome. And so this is the main chemical reaction that we're going to work with. Now, whenever you guys are performing these types of calculations, whenever a reaction is occurring, so whenever you are quantifying a reaction, okay, my personal suggestion for you is to convert everything to moles. Why is that? Why do we need to convert everything into moles? Well, if you guys look at the unit, for example, molarity. Molarity is a ratio of 2 units, moles per liter. You can actually do this calculation with molarity, but remember that you're adding volume to a solution that also has a specific amount of volume. And I personally don't want to recalculate the true concentration or the diluted concentration. There's just a lot more calculations to deal with. And so instead of looking at concentration in terms of molarity, I just want to deal with the amount. What is the raw amount of substance that I'm actually putting in my beaker? And so to figure out my raw amount, all I have to do is convert molarity into moles. And so to do that, I am going to take the concentration and I'm going to multiply it by its volume. And so if you guys are looking at this equation, if I multiply the volume in terms of liters, I can get these units to cancel out, leaving me with just the raw amount of that substance that's being put inside that beaker. And so that's exactly what I'm going to do. So I'm going to go ahead and calculate the moles of sodium hydroxide. And I'm going to go ahead and cross this sodium off. Remember, sodium is a spectator ion. And since the ratio is 1 to 1, the concentration or the amount is not going to change. Okay. And so if the concentration of my hydroxide that I'm putting in is 0.500 moles per liter, that's molarity, I'm going to multiply that by the volume that I'm putting in, or the volume that that I have of it. And so notice that this volume is in milliliters. I'm going to go ahead and express milliliters to its true value, which is times 10 to the negative 3. Right? So a milli is times 10 to the negative 3 liters. So this scientific notation represents milli. Okay. So that allows us to cancel both of these units of volume, leaving us with moles of hydroxide. So the moles of hydroxide is equal to 1.50 times 10 to the negative 3 moles. Okay. And so I'm going to go ahead and do the same procedure for my benzoic acid. And so notice I have 20 mils of this concentration of benzoic acid. So to calculate the moles of, and I'm going to start abbreviating benzoic acid as H-benz. So this is benzoic acid. That's going to be 0.500 moles per liter. So I grab that number from here, okay, of benzoic acid. And I'm going to multiply that by 20 times 10 to the negative 3. And that times 10 to the negative 3 is going to represent the milli. Now, if you guys knew that a milli, you can go ahead and move it 3 times to the left. You guys can do that. But I'm just showing all my work here. All right. And so the number of moles that I have in my solution of benzoic acid I apologize here. So I'm sorry, if you multiply 0.5 by 5 times 10 to the negative 3, that's going to give you 1.0, or this is hydroxide. Oh, geez. This is going to be 2.50 times 10 to the negative 3. Apologize about that. Now, if you guys multiply 0.5 times 20 milliliters, what you're going to get is 1.0 times 10 to the negative 2 moles of benzoic acid. So I'm just going to highlight this. I'm going to highlight this. Okay. And so these values represents, not only does it represent the number of moles of hydroxide, but the moles of benzoic acid, but it's representing the initial amount that you put in. Okay. And so this is going to be the initial amount that you put in this beaker. And so if we want to calculate the pH of the solution, we want everything in terms of when all of the chemical species is at, oops, what happened here? It's at equilibrium. And so what does that tell us? Since we want to calculate everything at equilibrium, and if we have initial amounts, it's telling us that we probably need to build an ice table to organize our work. Okay. So I'm going to go ahead and copy this. And I'm just going to go ahead and place it underneath here just so we can see all of the calculations without going back and forth. Let me move this just a little bit over. Okay, good. All right. And so it turns out that we can summarize this image that I drew here by creating an ice table. And so we have 2.50 times 10 to the negative 3 moles of the hydroxide. Okay, that's our initial amount. And then for this weak acid, this benzoic acid, we have 1.00 times 10 to the negative 2 moles. And so if you want to determine the equilibrium concentration, we need to define the change, and we need to determine the equilibrium based on the initial and the change. So a couple things here, since this is water, we can go ahead and completely ignore it. So if you guys recall, for equilibrium, we ignore anything that has a physical state of liquid or solid. Now, in previous equations, or I'm sorry, in previous word problems, we kind of have this notion that, okay, change is minus x plus x, da 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 da. However, if you look at if you take a step back and look at this problem, a reaction is occurring. So one substance is being consumed to produce the product. If you review the previous lecture videos, for example, on polyprotic acids or monoprotic acids, you basically only have one substance, and you're allowing it to do its own thing. You're allowing it to ionize by itself in a solution, basically in water. And if you guys are looking through those types of problems, the monoprotic and polyprotic acid calculations, there's no reaction that's occurring. And so we just don't know how much of it actually ionizes or dissociates. However, for these types of problems where a reaction is actually occurring, the change is specific. And so this is an acid and base reaction. And so whenever you have an acid and base reaction, both of these two components are just kind of like, they're gonna like battle it out. Like they're gonna throw all their chips in, and you know what, whichever one has the least amount will be completely consumed. Okay. And so if you think about it in that light, what the value between the two initial amount of moles is going to dictate what the change is. And so if you look at benzoic acid, notice that it's the number of moles is 1.00 times 10 to the negative 2. Whereas the number of moles of hydroxide is 2.50 times 10 to the negative 3. And so therefore, since this hydroxide has a lesser amount, so there's less amount of base and there's more amount of the acid, when this acid and base reaction occur, all the base is going to be consumed, right? It's just going to be completely consumed and taken over just because there's so much more acid in that solution. And so therefore, we're going to conclude that the change is 2.50 times 10 to the negative 3. And since all of the base is consumed, it's going to consume some amount of the weak acid, right? Because this is an acid-base reaction. So this is going to be like negative 2.50 times 10 to the negative 3, right? And so whatever is consumed, that's how much that will be produced. And so here in this case, we're producing 2.50 times 10 to the negative 3 moles, right? I guess I need to make sure I'm writing my unit here. Moles of the conjugate base. Now it also does produce, 2.50 times 10 to the negative 3 moles of water. But we don't really care about water just because it's never taken into consideration in the mass action expression. And so we have like this initial amount If this was like, I don't know, one of these Game of Thrones type of wars, right? So this is the number of people that we have initially, and then they are going to battle it out. That's the change. And the final outcome of that battle, in other words, if you add the initial and the change, so if you're adding downwards, notice that we have no more base left, right? So the base lost, the hydroxide lost. And so if you subtract 1.0 times 10 to the negative 2 to that of 2.5 times 10 to the negative 3, you get 7.5 0 times 10 to the negative 3. And remember, the unit is still moles. Okay. All right. Well, for the conjugate base, we have nothing to begin with, right? So if you read the problem, we only had this acid that's present in solution. And so here in this case, since we didn't have any conjugate base, we're going to leave the initial amount as blank. When we add downward, we produce 2.50 times 10 to the negative 3 moles. Okay. So each of these represent the equilibrium amounts. Now, if you guys take a closer look, and I do hope it makes sense in this first shot. At equilibrium, and I'm going to highlight this in orange, there is 7.50 times 10 to the negative 3 moles of the weak acid. And there is 2.50 times 10 to the negative 3 moles of the conjugate base. And so when, zoom in, when a solution has a weak acid and conjugate base present, what do we get? We have a buffer. And so if we have a buffer, what equation can we use? Now, if you guys said the Henderson-Hasselbalch equation, you're absolutely correct. And so remember that the Henderson-Hasselbalch equation also is one route to get us the value of the pH. And all we need to figure out is the pKa, and we need the ratio of the conjugate base to the weak acid. And yes, I did mention that there's like a bracket here in the previous video, so that represents molarity. But if you guys recall, if you have molarity, that represents moles per liter, and this is moles per liter. Okay, so that's what these brackets mean. So you don't actually necessarily need concentration in your Henderson-Hasselbalch equation. You can actually take out the volume and you're just left with moles. And so what you're going to put in is the equilibrium concentration, or the equilibrium amount, I apologize, not concentration, the equilibrium amount of the conjugate base and that of the weak acid, which from our ICE table we calculated. And so all we're going to do is we're going to take these two values and we're going to place them in their correct position in the Henderson-Hasselbalch equation. And so the weak acid, the 7.50 times 10 to the negative 3 moles, is going to go in the denominator, while the conjugate base, the 2.50 times 10 to the negative 3, is going to go in the numerator. So let's plug that in. So the pH is equal to the pKa plus the log. Now HA, which is our weak acid, remember this guy is our weak acid, and so this number represents the remaining weak acid we have left after the reaction occurred. So we have 7.50 times 10 to the negative 3 moles of H-benz, right? So this is our benzoic acid. And then at the top we have benzoate, or just benz. So that's 2.50 times 10 to the negative 3 moles of benz. Okay, so that's our conjugate base. That's really awesome. And so all we need to do is figure out the pKa. And once we have the pKa, we can plug it right in there and determine the pH. So what did my problem tell me? Okay. It told me that the Ka is 6.46 times 10 to the negative 5. And so to go from Ka to pKa, I simply have to apply the definition that pKa is equal to the negative log of Ka. And so if my Ka is 6.46 times 10 to the negative 5, I'm just going to take the negative log of it. And when I do so, my pKa is going to be 4.18977. I'm sure there's a whole bunch of numbers. Now, when we're going from Ka to pKa, remember that Ka has some significant figures, and whenever we take the p of anything, we're referring to decimal places. And so since I have 3 significant figures, that's going to represent 3 decimal places, or I need to report 3 decimal places. And so I'm going to go ahead and use the first 3 that I see after the decimal. And so if I round this value, my pKa is 4.190. Okay? So I'm rounding the 9 up, which rounds the 8 up. Okay. And so I figured out that my pKa is 4.190. All right, and so what I'm going to do is I'm going to reduce whatever is inside this parentheses. So if I divide those two values, I get 0.333 all the way to infinity. There's just a whole bunch of 3's. Okay. Now when I take the log of this, I'm going to get negative 0.477 1, 2, 1, 2, a whole bunch of numbers. And so I'm going to go ahead and take this value and add it to 4.190. So in other words, I'm subtracting them. Okay. And the resulting pH that I get is going to be 3.71265, a whole bunch of other digits. And so in this case, I'm going to make sure I report 3 places after the decimal. I'm adding here, right? So I have to apply rules of addition for sig figs. And so my final answer is going to be pH is equal to 3.713. Okay. It's a crazy calculation only for one number. And so let's look back at the problem and see if all of this makes sense. And so we have this acid, right? This benzoic acid. And what we're going to do is we're going to add some sodium hydroxide. And so when we add that sodium hydroxide, an acid-base reaction is going to occur. Excuse me. And after everything is in equilibrium, it turns out that the resulting pH is going to be 3.713. Okay. And so just to review very quickly, like how do I know that I'm supposed to do all of this stuff? Like what are the clues? And so once again, we want to calculate the pH at equilibrium. Since we want to calculate the pH at equilibrium, that automatically suggests that we're going to have to build an ice table because we need to know those values at equilibrium. And so if you read through the problem, we have a base reacting with an acid. And so since there's an actual reaction that's occurring, we need to know the initial amounts. And then from the initial amounts, we're going to determine the change by whichever one is the least. And so it turns out that 2.50 times 10 to the negative 3 is less than 1.0 times 10 to the negative 2. And so the base is going to be completely consumed in the course of the reaction. And since we have more acid, then there's still going to be a remainder of acid that remains. And so that's the 7.50 times 10 to the negative 3. And then, we're going to produce that amount of product. In this case, it's the conjugate base. And then once I've realized that I'm left with a weak acid and its conjugate base, this is simply a buffered system. And so if I have a buffer, then I can use Henderson-Hasselbalch equation to figure out the pH. Okay. And so hopefully that review helps you kind of like digest the main points in our calculation. All right, so it's kind of like a slow start. Just want to make sure that everybody's kind of on ball with me here. And so let's go ahead and pick up the pace by looking at another problem. And so for example number 2, we're going to determine the pOH of a buffer made by mixing 133 mils of 0.0270 nitric acid to 172 mils of 0.0570 molar sodium acetate solution. And so the Ka of acetic acid is 1.77 times 10 to the negative 5. All right. And so let's kind of break this down. So we are going to determine the pOH. So that means that we need to determine everything that's at equilibrium. And whenever you want to determine things that's at equilibrium, it invites this idea of using an ice table, right? We're trying to solve for E in that ice table. And so we have nitric acid. So I'm going to skip over like the numbers. I have nitric acid, and I'm reacting it, or I'm putting it in a solution of sodium acetate. And so it says in its name, nitric acid and acid, but acetate is the conjugate base of acetic acid. And so what we have here is an acid and base reaction. Okay. And so automatically we have to develop a chemical equation that's representative of this acid-base reaction. So let's go ahead and do that. So we have nitric acid, which is HNO3, and then we're going to go ahead and react it with sodium acetate. And so acetate is going to be C2H3O2. I covered that in a earlier video. Okay. And so right now it's just kind of weird on how this this reaction might occur. But if you guys remember your first semester general chemistry, if we have a cation and another cation, we can do like a double displacement reaction where we switch the positions of these guys and we get sodium nitrate and that of HC2H3O2. Okay, so I'm simply switching the positions of my cations, and everything is the charge of every single ionic species is either -1 or +1. So everything is already naturally balanced. Now, if you want, you can write a net ionic equation. And so in this net ionic equation, we're going to go ahead and take away our spectator ions. Remember, sodium nitrate, they're soluble. And so we're going to go ahead and cross them out. Now, if you guys didn't cross them out on your own, you guys should still be fine in terms of figuring out the solution to this problem. Let's see here. So I'm going to go ahead and cross them out. So I only have my strong acid reacting to my C2H3O2. And this is my weak base. Okay. And the compound that I get with an acid reacting to a base is going to be HC2H3O2. Okay, so when you guys are reviewing this video, I want you guys to compare and contrast these chemical equations that I'm writing if a strong acid is added or a strong base is added to the solution. Okay. And so since I'm reacting a strong acid to a weak base, and if I want to determine the pOH, I need everything in terms of equilibrium, right? Everything needs to be expressed at equilibrium. And so that invites me to determine the initial concentration so that I can somehow figure out the equilibrium concentration. And so I'm going to go ahead and highlight this in a different color. Let's do pink. I have 133 mils of my nitric acid. Okay. And so whenever you're doing these types of reactions, I really do encourage you to just convert everything into moles and work with moles. And so for my nitric acid, or just, well, I'll go ahead and write that down, NO3, and I'm just going to put in parentheses H+, because that's representative of this substance here. Okay. I have 133 mils. So remember that is the same as 133 times 10 to the -3 liters. And I'm going to multiply that by the molarity, which is 0.0270. And this is moles per liter. And so if I cancel that out, the number of moles of acid that I have is going to be 3.591 times 10 to the negative 3 moles of my acid, my H plus. And so I'm going to go ahead and write that right underneath my equation. So I have my initial. So that is 3.591 times 10 to the negative 3 moles. Okay. Now, I also need an initial value for my weak base. And that's going to be described by this value. So I have 172 mils of 0.0570 molar of sodium acetate. And so I have my sodium acetate. Oops. I can go ahead and just cross this out because I know my sodium is a spectator ion. And so I have 172 times 10 to the negative 3. That's the same thing as a milliliter. Times this by its concentration in terms of moles per liter. So that's going to cancel, and I simply get 9.804 times 10 to the negative 3 moles, okay, of my acetate. So that's going to go ahead and be placed as my initial amount. Now, did the problem state that I have an initial amount of my conjugate acid? Okay, and if you said no, you're correct. The only other value that this problem gave us is the Ka, which we'll use later. And so since this problem didn't give us any indication that there was an initial amount of conjugate acid, we're going to go ahead and blank that out. Now, let's go ahead and talk about the change. And so once again, we have an acid reacting to a base. And whenever you have an acid reacting to a base, there's one substance will be consumed. Actually, both substances will be consumed. However, the change in this scenario is going to be dictated by the substance that has the least amount. And so if you look at the magnitude, it's times 10 to the negative 3 times 10 to the negative 3. And so therefore, we're going to look at the values. So 3.591 and 9.804. And so it looks like 3 is less than 9 since they both have the same magnitude. And so therefore, it looks like all of the strong acid that was added into this solution is going to be consumed completely, right? And so we're going to consume 3.591 times 10 to the negative 3 moles. And we're also going to consume 3.591 times 10 to the negative 3 moles. Okay. So this amount of this amount of this strong acid will react with this amount of the base. So it's going to be consumed. And so since this substance is a product, we're going to produce 3.591 times 10 to the negative 3 moles. All right, and so now that we have determined the change, we're going to discuss equilibrium. And so if you add downwards, notice that we don't have any more strong acid at equilibrium. So it's completely consumed. Um, and so if I subtract downwards or add downwards, which will invite a subtraction, it's going to be 6.21 times 10 to the negative 3. And this is going to represent moles of C2H3O2 with a negative charge. Forgot to put that negative charge up there. And so if I add downwards, I have 3.591 times 10 to the negative 3 moles. In this case, it's going to be HC2H3O2. All right, so if I look at what I have my weak base. Okay. At equilibrium, I have a weak base that's present. And I also have the conjugate acid of the weak base present. And so whenever you have a weak base with a conjugate acid, what type of solution is this? Dun dun dun, it's a buffer. Okay. And so for us to calculate the pOH, we're going to have to use a different equation, but it's very related to the equation that we've been using over and over and over again. Instead of solving for pH, we're going to solve for pOH. And when you're using the Henderson-Hasselbalch equation for the pOH, we need the pKb, not the pKa. In addition, the positions of the conjugate acid and the conjugate base switches. And so notice that one way to memorize this is, if you're solving for the OH, that base needs to be at the bottom. And so therefore the weak base must be in the denominator and leaving the conjugate acid in the numerator. Okay? And so if you guys look at the Henderson-Hasselbalch equation, for pH, notice that H is here and HA is representing the acid. Right? So the acid is in the denominator and the base is in the numerator. Okay. All right. And so all we have to do to figure out the pOH is plug everything in, make sure that we have the pKb, and then we're done. And so let's go ahead and execute this. And so since they're ratios, since the conjugate acid and the weak base are ratios of each other, we do not need this in molarity. We just need this in moles. All right, so the pOH is equal to the pKb plus the log of the weak base. In this case, is going to be 6.21 times 10 to the negative 3 moles. I'm just going to put in B minus to represent my base. So I'll put B minus here to represent that. Now, if you guys wanted to put A minus, just to be consistent, you guys can. Maybe I'll just be consistent, just use A minus. Okay. And so the conjugate acid, I'm going to represent that whole thing as HA. That's going to be 3.591 times 10 to the negative 3 moles of HA. And obviously these units will cancel. That's the powerful thing about these these ratios, and I simply get the pKb is equal to the log of 0.5778206. So I just divided those two numbers. And if I were to take the log of that value, I would get negative 0.237997. And so since I have 3 sig figs here, I just need to keep 3 sig figs all the way through. And so here in this case, I can go ahead and just round this to negative 0.238 if I want to. Shouldn't change our answer by too much. And so the only thing that I need to figure out is my pKb. And so it looks like the Ka, ooh, what happened? It looks like the Ka is 1.77 times 10 to the negative 5. And so if my Ka is equal to 1.77 times 10 to the negative 5, I need to convert this into pKa. And from pKa, I can get my pKb. And so I'm simply going to take the negative log of 1.77 times 10 to the negative 5. Let me see here. So my pKa is equal to 4.752026, a whole bunch of numbers. And once again, sig figs, I have 3 sig figs, 3 sig figs, 3 places after the decimal. Okay. And so remember that little trick. I have Ka. If I want to convert that to pKa, I know that Ka takes a look at significant figures or significant digits just in general, and pKa takes a look at decimal places. So if I have 3 sig figs, I need 3 decimal places. And so my pKa is equal to 4.752. I'm going to round, the 0 is not going to round the 2 up. And so my pKa plus my pKb is equal to 14. And so if I plug this number into pKa and then subtract it over to the other side, my pKb is going to be 9.248. Okay. So now that I've figured out my pKb, I'm going to go ahead and plug that into here. And then when I subtract those two values, my pOH of the solution is going to be 9.00997, whole bunch of numbers. I'm going to subtract with 3 places after the decimal, so I need to keep 3 places after the decimal. So pOH is going to be 9.010. Okay, so this 9 rounds that 9 up, and that 9 rounds that 0 up. And so this is going to be the pOH of my solution after this acid-base reaction occurred. Okay. Cool, right? Okay. All right. And so if you look at example number 2 and example number 3, example number 2 and example number 1, Notice that it gave us the concentration of one component in the solution, like benzoic acid or sodium acetate. Actually, before the reaction happened, you guys didn't actually have a buffer. You guys just had a solution of sodium acetate, and then adding in that nitric acid produced that buffer. And so what we're going to look at is one more example. This example is just a little bit challenging. The reason why is because this example is already a buffer to begin with. And so in the first example and the second example, you didn't have a buffer, you just had a pure substance. And then you performed an acid-base reaction, and then you got a buffer. So let's go ahead and read through this problem. You have a beaker that contains 175 mils of a 0.100 molar acetic acid acetate buffer that is already at a pH of 5. And so if a student adds 8.40 milliliters of a hydrochloric acid solution, what is the pH of the solution? Okay. And so once again, since the question is asking us to determine the pH of the solution, everything has to be at equilibrium. And the only way to quantify those the equilibrium values is to use an ice table. And so that means that we need to determine the initial amount. And after we determine the initial amount, we need to think about how this reaction is going to proceed. So what is the change? And then last but not least, we need to think about the equilibrium, or we need to determine the equilibrium concentration by adding the initial and the change. All right. And so let's go ahead and let's just draw a picture for now. Let's visualize this. So here we have a beaker, and it says that you have an acetic acid and acetate buffer. And so I'm going to represent acetic acid as my HA, and I'm going to represent acetate as A minus. And so it turns out that we already have a buffer that's present in this solution. Okay, we already have a buffer. And then you're going to add hydrochloric acid. Okay. And so when you add hydrochloric acid to this solution, which of these two ions is going to be the active component? And so if you said hydrogen, then you're absolutely correct. Remember that Cl or chloride doesn't, since it's the anion of a strong acid, it's not going to affect the pH of the solution. And so you're simply dumping in more acid. And so if it's an acid that you're adding, what is it going to react with? And so it's going to react with a base. And the base in this case is going to be your acetate. Okay. And so to summarize what's happening here, we're going to have our acid, H plus, reacting with our base, which represents A minus. Remember, A minus is acetate. And that's going to come together to produce HA. And HA is going to represent acetic acid. And so this is our strong acid. This is our weak base. And what we're going to produce is the conjugate acid, which turns out to be weak. So it's the conjugate acid. Okay. So this is our overall chemical reaction. And We're going to use this overall chemical reaction to organize our train of thought. I'll just do it here. Actually, let me copy and paste. No, it's okay. All right, so I have my acid, which is represented by H+, and then I have my base, which is represented by A-. So this is the acetate. And then it's going to produce, so this is our product, HA, which happens to be our conjugate acid. All right, so since our goal is to determine the pH, which requires us to determine stuff at equilibrium, that means that we need to write an ice table. Okay. In other words, we need to determine the initial concentration, we need to determine the change, and we need to determine the equilibrium amounts. And so let's go ahead and look at our problem. Let's look at the numbers now, and let's see if we can calculate the initial concentration. And so I'm going to go ahead and look at the acid first. Okay. So we're adding this amount. And so for our HCl, or simply our H+, we're going to go ahead and take 8.40 mils. I'm going to convert that into liters. So that's 8.40 times 10 to the negative 3 liters. And I'm going to go ahead and multiply that by the concentration, which in this case is going to be 0.300 molar, or 0.300 moles for every 1 liter. That cancels out. So the number of moles that I get for my H+ is going to be 2.52. Let me check that actually. So it's going to be 0.3 times this by 8.40 times 10 to the negative 3. Yeah, so it's going to be 2.52 times 10 to the negative 3 moles of H+. So that's the value that I'm going to place in the initial amount. So 2.52 times 10 to the negative 3 moles. All right. So let's go ahead and talk about the initial amount for the base, HA. And so we have 175 mils of a 0.100 molar concentration of acetic acid and acetate buffer. And so if you look at that phrase, what I boxed, notice that it didn't really specify acetate. It specified both. So what does that mean? That means that this is the total concentration of acetic acid and acetate. And so this is telling us that if I were to add acetic acid, the molarity, the concentration of acetic acid, to that of the base, the acetate, I get a 0.100 molar concentration. And so there's no other items inside the problem that specifies what the exact concentration is. And so what we're going to have to do, so whenever you guys fall upon this situation, when you're given the total concentration of both of the acetic acid and acetate buffer, what you want to do is you want to figure out the ratio between acetic acid and acetate. And this is just a technique. I know I just kind of threw it out there, but it's something that you're going to recognize as you work through these problems a little bit more. And so I'm going to kind of perform a side calculation here. I'm just debating where to place it. I'll go ahead and place it here. And so whenever you have a total concentration, so I'm going to go ahead and rewrite that. So I have my acetic acid, and remember I abbreviated acetic acid as HA, and I have my acetate, and remember I abbreviated acetate as A minus. The sum of those two concentrations gives me the total concentration of 1.00 molar. Okay, so therefore I have an equation that I can use to figure out the exact concentration of each one. But the problem is that I have two unknowns. And so to figure out the two unknowns, we're going to utilize the Henderson-Hasselbalch equation to determine the ratio of acetic acid to acetate. And this is a tool that's always available to us if we're given the pH and pKa. And so the pH is equal to pKa, or the Ka actually. So if we're given the Ka or the Kb, we can figure out what the pKa is. The log of the ratio of my base to my acid. And so according to the problem, I have a pH of 5. Okay. And my pKa is 4.752. And so I'm going to go ahead and plug in those numbers. So I have 5.00 is equal to 4.752. And that's going to equal, or I'm sorry, that's not going to equal anything just yet. And so we're going to add log of A minus over HA. And so we're going to solve for the ratio of this. And you'll see why in just a second. And so I'm going to move this guy over to the other side. So that's going to give me a value of 0.248. And that's going to give me the log of the ratio of A minus over HA. Now I'm going to take the base 10, the anti-log of both sides. And the ratio of my A minus to my HA is going to be 1.77. Okay. Now check this out. If I take this HA and multiply it to the other side, I'm going to get 1.77 times this by the concentration of HA. And that's going to give me the concentration of my A minus. So what I just created is an expression to define the concentration of the base. Well, what I can do now is plug in what the concentration of the base equals to wherever I see the base. Right? So did you guys catch that? And so since the concentration of the base equals this expression, I can plug this expression into this equation so that everything is in terms of one variable. Okay, so the result that I get is going to be HA plus 1.77 times this by HA equals to 0.100 molar. And basically if I have a variable, I have one of it. So 1 plus 1.77 is going to be 2.77 HA. That's equal to 0.100 molar. And then I can go ahead and divide 2.77 to the other side. And so the concentration of my HA, and remember this is representing the initial concentration, that's going to equal to 3.61 times 10 to the negative 2 molar. Okay. And so now that I have the concentration of my HA, I'm going to go ahead and plug in that value to figure out the initial concentration of my A minus. And so I'm going to go ahead and plug this value in here, right, in this equation. Okay. And so remember that HA plus A minus is equal to 0.100 molar. Now that I know my initial concentration of HA, I'm going to go ahead and plug that guy in there. And I'm going to get 3.61 times 10 to the negative 2 plus A minus, which equals to 0.100 molar. And so I'm going to move this guy to the opposite side. So A minus is equal to 0.100 minus 3.61 times 10 to the negative 2. And the concentration of my A minus, and remember this is still initial concentration, is going to 0.1 minus 3.61 times 10 to the negative 2. That's going to give me 6.39 times 10 to the negative 2 molar. And so just to summarize my results, this is what I'm going to highlight. Okay. Now, this is new. This is a brand new concept. Well, not so brand new. You guys did this in algebra. But, in the context of the word problem, I was able to determine the unknown concentrations, the composition of my HA and A minus, once I was able to figure out the ratio between them, right? And the ratio can always be determined by using the Henderson-Hasselbalch equation if you are given the pH and some form of an equilibrium constant that you can convert to pKa. Okay. And so once I plug this definition into A minus, I was able to get this equation. You add everything up and then you just divide, and that's going to give you the initial concentration of HA. Then you plug this guy back into the original formula to get A minus. Okay. So now that I have the initial concentrations of each component, I'm going to go ahead and write that down here. Okay. Now it turns out that we're still on I, right? The initial concentration is for my A minus. Let's do A minus first. Okay. It was 6.39 times 10 to the negative 2 molar. And so if I want to convert this into moles, I need to still multiply it by the volume. And so 175 milliliters is the same as 0.175 mils. So I'm going to skip a couple steps. So 0.175 liters times this by 6.39 times 10 to the negative 2 moles per liter. So that's going to give me 0.175 times the answer. So that's going to give me 1.11825 times 10 to the negative 2 moles. And so I just need to report the correct number of sig figs. So I just need 3. So this 8 is going to round that up. And so the total number of moles that I initially have is 1.12 times 10 to the negative 2 moles of my acetate. Okay, my A minus. Now, if you guys looked at the result, we actually have an initial amount of our conjugate acid, or HA, and the concentration is 3.61 times 10 to the negative 2. And so we cannot leave this item blank because in the problem, we already have a buffer system already prepared for us, like we didn't create one. And so that means that we do have an initial concentration of our conjugate acid. And that value was 3.61 times 10 to the negative 2 molar concentration. And so very similar to what I did in the previous step, I took the volume, so the volume is the same, 0.175 liters, and I'm going to multiply it by the concentration of my conjugate acid. So this is going to be 3.61 times 10 to the negative 2 moles for every 1 liter. Okay. So the volumes are going to cancel out when you multiply across. You get 0.175 times this by 3.61 times 10 to the negative 2. And you get, let's see here, 6.32 times 10 to the negative 3 moles of HA. And so this is going to represent the initial amount, that we are going to place in this box. So we have 6.32 times 10 to the negative 3 moles. Okay. All right, and so now that we have the number of moles, the initial moles, we're now ready to talk about our change here. And so at this point, this is kind of like clockwork. This is similar to the other 2 problems that we worked on. If you guys look at the value of the moles, we have this acid that's times 10 to the negative 3, which is lower than times 10 to the negative 2, which is a higher amount. Okay. And so in this case, all of our acid is going to be consumed. And so we're going to subtract 2.52 times 10 to the negative 3 moles. And we're also going to subtract 2.52 times 10 to the negative 3 moles. So remember, this is like a 1-to-1 ratio, right? And so we need to consume this amount of the base if we're going to consume this amount of acid. Okay, that's a neutralization reaction. It's a 1-to-1 ratio. And we're going to go ahead and create 2.52 times 10 to the negative 3 moles of HA. Now we're just going to tally everything up. Notice that we completely consume our acid. For the second column, I'm going to take 1.12 times 10 to the negative 2 and subtract it by 2.52 times 10 to the negative 3. Okay. And so in this case, I get 8.68 times 10 to the negative 3 moles of my A minus, my acetate. Okay. And for the last column, I'm going to add 2.52 to 6.32. So 6.32 times 10 to the negative 3 plus 2.52 times 10 to the negative 3. Okay. And then that's going to give me 8.84 times 10 to the negative 3 moles. Okay. And once again, that's going to represent my HA, which is my acetic acid. Okay. And so once again, if you guys look at the equilibrium, what we have at equilibrium, we have acetate and acetic acid. Okay, so they're still present in my solution. And whenever you have the a weak base and a conjugate acid, or vice versa, a weak acid and a conjugate base, we get a buffer. And we can go ahead and use the Henderson-Hasselbalch equation to figure out the pH of the solution. Okay, and so we started off at 5, but then when we added our acid, it's going to change the pH of the solution, and we're going to see by how much. And remember, buffers resist changes to pH, so there should still be a change, but not a significant amount. And so let's go ahead and go through the motions. The pH is what we're going to solve for, and this is representing after the addition of the acid. Okay. And that's going to equal to my pKa plus the log of A minus over HA. And so what we're going to do is we're going to place them in the correct place. So pH is equal to pKa plus log. And then A minus is going to be 8.68 times 10 to the negative 3. And then we're going to divide that by 8.84 times 10 to the negative 3. And so once again, this is going to be our A minus, just to show my work. And this is representing my HA. And the units are both in moles, but since they're ratios of each other, they're going to just cancel out. And the pKa, it was already given to us in the problem. We didn't really need to solve it. It was 4.752. And just to kind of prove it to you, it's right here. I just circled it. It's already given to us in the problem. Okay. All right, and so we're going to go ahead and divide these two values that's inside the parentheses. So we're going to take 8.68 times 10 to the negative 3. And then we're going to divide it by 8.84 times 10 to the negative 3. And what I get is going to be the log of 0.981900, a whole bunch of other numbers. And so I'm just going to put a little mark above the 1 to remind me that I'm keeping 3 decimal places. So just this much. Now, when I take the log of that value, I get negative 7.9325 398, some other numbers, times 10 to the negative 3. And so since I'm taking the log of the number, I need to report the correct number of sig figs, 3 sig figs, 3 decimal places. Okay. All right, and so I'm going to go ahead and add that to 4.752, which is the pKa. And so how is this ratio going to affect my pKa? Okay. Now, if you guys look at the values, 8.84 is much greater than 8.86. And since we're talking about the pH scale here, we have more acid than base. So does it make sense that our log is negative? Yes, because we have more acid, and on the pH scale, if we have more acid, we decrease the pH. And so we're going to take 4.752 and we're going to subtract it. We're going to add it to our answer. So let me just do the calculation over again. Sorry. So 4.752 plus negative 7.933. Oh, times 10 to negative 3. So 4.752 minus 7.933 times 10 to the negative 3. And so the pH is going to be 4.744. Okay. And so we did all of that calculation just to end up with, we did all of that calculation just to observe a very minute change in our pH. All right, it's so small. It's a difference of this amount. Okay. However, that shows you, or that demonstrates, that buffers resist changes to pH. Okay. Oh, actually, you know what? Hold on. Let me take that back. The original, sorry. So here, I don't take it back completely. I just forgot that the original pH is 5. And so we didn't really, and so the original pH is 5.00. And after we added some acid, some hydrochloric acid, it decreased to 4.744, which is still not a lot in terms of pH units compared to not having a buffer. So if we didn't have a buffer, the change in pH would be so dramatic. It would be like, I don't know, in the 1 or 2 range. Okay. So hopefully you guys kind of followed my logic. This one was a doozy just because the problem already gave me the total concentration. So we already had a buffer present, and I had a total concentration. And so the trick to this problem is determining the ratio of the acid to the base so that you can plug it in to this formula to determine the initial concentration. All right, and so I'm going to leave you guys with just one last problem. I'm not actually going to do it. I want you guys to either pause this video or take a snapshot of this video. And so a beaker contains 200 mils of a 0.100 molar acetic acid, acetate buffer, that has a pH of 5, right? So it's very similar to the previous problem. If a student adds 6.30 milliliters of a 0.490 molar hydrochloric acid solution, what is the pH of the solution? And so I've changed some numbers around. I gave you guys a pKb instead of pKa. And so I want you guys to tackle this on your own. And then there's some checkpoint answers. See if you guys are doing it correct. And so before the hydrochloric acid was added, this was the initial moles of acetate and acetic acid. And so if you guys did the first part correct, and if you guys convert molarity to moles, this should be the initial moles that you guys will get. And after the acid was added, this is the number of moles of acetate and acetic acid. So this is the equilibrium values. And then after you guys, so now that you guys have determined the equilibrium values for acetate and acetic acid, when you plug it into the Henderson-Hasselbalch equation to determine the pH, it's 4.725. And so in this scenario, if we added 200 mils, if we have 200 mils of the buffer, and we're adding 6.30 mils of the hydrochloric acid solution, then we're going to get a pH of 4.725. So we're starting off with 5.00, and this is the final pH after we add that acid. So go ahead and do this on your own. Feel free to rewind any part to this video. These are just advanced problems. They're going to be, some form of it is going to be on the exam, that I can guarantee. So get some practice. If you have any questions, email me. The next video takes a look at buffer preparation. So we're going to go further and use the Henderson-Hasselbalch in another perspective. All right, guys. Catch you later. Bye.